Okay, so in this video, I am going to talk about what might be the most important idea in really understanding the physics and mathematics behind music. And the idea has to do with what I mentioned last time, that if we want to understand some complicated looking time graph, this is the displacement of air versus time in a sound wave. If we want to understand that and decipher it and understand, it's like the difference between the graph for a saxophone note and for a trumpet note, for a piano note, or even actually for more complicated sounds, combinations of instruments or sounds that aren't even musical notes, then the way that we can do that, a very, very nice way that we could do that, is to realize that complicated time graphs like this can actually be decomposed into simple parts. And these parts are going to be the pure tones or the pure sinusoidal waves with different frequencies and amplitudes. So to begin to explain that, I want you to think about the following question. So in this question, we have two wave pulses. Maybe this graph represents the displacement of air in a couple of sound waves, or maybe they're wave pulses traveling down a string. And the question is, what is going to happen when those wave pulses meet each other? And so will they bounce off and reflect backwards? Will they destroy each other, maybe leaving just a few random ripples? Or will they pass right through each other? So maybe just pause for a minute, think to yourself what you expect, and then we'll talk about the right answer. Okay, so in order to answer this, I'm going to actually do a demonstration. It'll be a simulation using the wave simulator that I've showed you before. So what I have here is our wave simulator again. And on the left, I have it set up so that when I press the green button, it'll create a wave pulse that travels down the string, and it'll bounce back once it hits the pole at the end. What I'm interested in here is to see what happens when two wave pulses come together. And so I'll create a second wave pulse when the first one is about to come back, and then we'll see what happens as they approach each other. And here we go. So there it was. We can watch it a few times. And let's do it one more time in slow motion. A little bit faster. Here we go. And so they come along, and basically what you see is they just add up temporarily. But then after the pulses pass by, it's as if they never encountered anything. It's just as if they were traveling back and forth on the string on their own. Okay. So what we observed in the simulation is that the wave pulses traveled right through each other. Those are waves on a string. Now you might not believe me, that was just a simulation, and so I could make that do whatever I want, but it's actually an accurate simulation. And if you don't believe me, let me try to convince you by just talking about another example. And so what I want to think about is the situation where you and another person are facing each other and you happen to be talking at the same time. And so you're both producing these sound waves, they're traveling towards each other, they will meet in between you, and if those bounced off each other and reflected backward, well then you would only hear the thing that you said and not the thing that the person you're talking to said. If the sound waves destroyed each other in the middle, then neither of you would hear the other person. But you know what happens if you're talking to someone else, then you both continue to hear each other. I mean, you can hear both what you say and what the other person says. You might not be able to understand it if there's all that noise going on at once, but our experience tells us that it doesn't really matter if there's other noises happening. When I speak, my sound is still going to reach the other people. Okay, and so you could have lots of different sounds all propagating through the same air, and they don't mess each other up. They don't destroy the other sound waves. They don't cause the other sound waves to bounce off in weird directions. So this is actually a reflection of a very fundamental and important principle in physics, particularly the physics of waves, which is called the principle of superposition. And that says that multiple waves can travel on the same medium, whether it's air or a string or the surface of the water, at the same time without disturbing each other. So we could be a little bit more precise about that. And what we can say is that the displacement of your medium, like the displacement of the air molecules, due to multiple waves at the same time, it's just the sum of the displacements of the individual waves. And so if I want to know what's going to happen with these two waves, well, when they come together, the displacements will simply add up. And then after they've come together, the displacements will be the same as they would have been before, because this one will just be added to the zero displacement that is present in the other wave after this pulse has passed. So let's do an example using the principle of superposition. So what I want you to do is try to imagine what the time graph for a wave will look like if we have one low-pitched pure tone that has a larger volume. I'm going to make that using this tuning fork, and I'll put the tuning fork close to the microphone. And then the other thing we're going to have is a quieter but higher pitched pure tone, which I will make by whistling. And we're going to have those go at the same time. And I want you to try to think about what will the shape be when we actually display that time graph using the Audacity software. Okay, so well, let's just do it and we'll see what happens. There we go. So let me zoom out again. And actually, I'll record each of these separately, and then I'll record them together. Okay, so let's first do this one. Okay. And then I will actually continue with the same recording. I'll do a whistle. Okay. So maybe we can just have a look at what those look like quickly. And so there's the time graph for my tuning fork, and I'll slide this over now and have a look at the time graph for the whistle. And so you see the time graph for the whistle is also pretty much a pure tone, and it's got a smaller amplitude. Okay, so now what I'm going to do is I'm going to start again and record both of those on top of each other. So play the sounds at the same time, and we'll see what the time graph looks like. Okay, so here we go. Let's just zoom out, and I'll start the recording. Okay. I'm not the best whistler in the world. So let's pick this point here where I had the whistle going and I had the tuning fork going, and we'll zoom in on that. Okay. And so it's kind of amazing. It's just what was promised by the principle of superposition. Okay. And so what you have here, it looks like just little ripples on a big ripple. And it's really mathematically what it is that you have the time graph coming from the tuning fork, which was the larger period, higher amplitude sinusoidal curve. And then on top of that, you have the short period sinusoidal curve with a small amplitude. And if you add those together, then it basically looks like this. And so you could see the up and down happening at the short time scales that had to do with my whistling. And then we have the up and down on the longer time scales that had to do with the sound of the tuning fork. And so this particular time graph, that's what it looks like when you have a low-pitched, higher volume sinusoidal sound, pure tone, and a quieter, high-pitched tone. And that's what we kind of expected using this superposition principle. Okay, so if I just have a look at those three graphs all at once, then you could see that if you added this one to this one, then you would just be kind of rippling up and down, but then overall following the path of this original sinusoidal graph. Okay, so now I want to show you a special thing that happens when we add sinusoidal graphs, but we make the frequency of one of them to be a multiple of the frequency of the other. Okay, so here's a quick question for you to think about. Suppose we add two pure waves, one with a frequency of 100 hertz, period of 0.02 seconds, and another with a frequency of, this should be, the first one should have been 50 hertz, and the second one should be 100 hertz, period of 0.01 seconds. Okay, so which of these options is true? Will it still be periodic? And if so, the combined thing, what period will it have? Okay, so the right answer is that it will still be periodic, and it will have a period of 0.02 seconds. The way to understand this is that the first pattern, it repeats every 0.02 seconds. The second pattern repeats every 0.01 seconds. But you see, because it does that, it also repeats every 0.02 seconds. So every 0.02 seconds, both patterns will be starting again. And so altogether, we're going to get something that will definitely repeat every 0.02 seconds. And so that has some very interesting consequences that I'm going to show you in another simulation. So what I have here is something that allows me to add up pure tones, but not just any pure tones whose frequencies are multiples of some basic frequency. So the second panel here shows the time graph for a particular pure tone. We could listen to that. It sounds like this. Okay, and I can control the amplitude of that using this slider here. So a little bit quieter, louder. Okay, so not particularly pleasant. But I could also turn that one down, and I could add in a pure tone which has exactly twice the frequency. So you see that compared to the original one, the period is half as much as before. Okay, and we expect that's going to sound higher. Okay, so musically it's actually an octave higher. We're going to be talking about these relationships between different musical notes and intervals later on. But for now, we just have this note that's a higher pitch. But there's something really interesting that happens if we have both of these things at the same time. And now what we're looking at here is in the second panel, it's the two separate sinusoidal waves. Those are the two separate time graphs. And then in the bottom panel is the combination of those two. If I just add the displacements from each of the two, then I get this bottom graph. And what you notice is that as I turn on the one with twice the frequency as before, then we start with a sine graph, but what we end up with is something that's actually still periodic with the same frequency as before. And so what we learned is that if you had something that's periodic, it should sound like a musical note with the frequency determined by 1 over the period. And so we have the same period or the same frequency as before. So this should just sound like a different timbre of musical note compared with the original note. And so let's hear what that sounds like for some example. So this particular shape. Okay, so that's what it sounds like. And then I'm going to turn off the second part. Ready? Okay, so you see that it didn't really sound like two different notes as you might have thought. It actually sounds like one note with a different quality. And we could do that also with some higher frequencies. So if, say, the bottom one is 100 hertz and this is 200 hertz, then this might be 300 hertz. And so we could just add various sound waves with multiples of the original frequency. And what you see is that I get a different shape, but it's still periodic with that same period as in the original case. And so let's hear what this one sounds like. Okay, so again, that sounds the same note basically as the original one, but it sounds different. It sounds like a different instrument as compared to the original sine wave or that first sine wave I played. So I can play around and add all of these different frequencies, and as long as they're all multiples of that original one, I'm going to get some kind of a note that's the same note as the original one with a different sound quality. Okay, and so one of the amazing things is that if you start with a pure sine wave with a certain period, and then you allow yourself to add other sinusoidal waves with multiples of that frequency, and you play around with the different amplitudes, then it turns out you can get absolutely any shape you want of that period. And what that tells you is that basically any kind of musical note, the C played by a saxophone or by a piano or by a guitar, you can actually decompose that into sinusoidal waves. So notes with different timbre are actually different combinations of pure tones with some basic frequency that we call the fundamental frequency, and then with some multiples of that frequency that we call harmonics of that fundamental. Okay, so let's just get rid of that one. And let me just summarize the important lesson of that video. So I'll say it in two different ways. The first way I'll say it is a mathematical way, and the second way I'll say it is a conceptual kind of musical way. So what we were discovering in that video is that if you add up pure tones with some frequency and some multiples of that frequency, then you're still going to get something which is periodic with the period of the original one. And it turns out that any time graph, so conversely, if you start with any shape with a certain period, that you could actually in some way get that by adding up pure tones, with the frequency of your original graph plus double that, double that, 3 times that, 4 times that, etc. Okay. And this basic frequency that we have in our periodic graph, that would be called the fundamental frequency for that note. And what we would say musically is that this particular note, that note on the saxophone, is a combination of that fundamental frequency plus a certain amount of this second harmonic and third harmonic and fourth harmonic. So these higher frequencies are referred to as harmonics of the fundamental frequency. So what does this mean in practice? It means something amazing, which is that when you have different instruments playing the same musical note, so we have a saxophone playing 100 hertz or a cello playing a note with 100 hertz, then basically the difference between those is just which combination of pure tones they are. Each one of these notes, the note on the saxophone, is exactly equivalent to a certain set of pure tones being played on top of one another. So in principle, I could have a collection of these tuning forks that play pure tones, and if I chose the frequency, if I chose the frequency of the lowest one to be the same as the note on the saxophone, and then I chose the higher ones to be multiples of that, and I picked the right amplitude for each one, then according to this, the combination of those things would sound exactly like a saxophone note. And we could do the same thing for a cello note or a piano note. And so when we're talking about different kinds of timbres of musical notes, then it's very convenient to talk about them in terms of how much of each harmonic is there in that note. So we'll get back to that in more detail in the next video and future videos.